I said no. I said Brian's just going to give a
I will
seminar
when I
online.
can.
Yeah, but
As soon as I can.
Yes.
Now, what's his name? Remind me his name.
Yong Y-O-N-G, and John is same surname as mine. He published a review article on hard-to-meet alloys in the Progress of Material Science a few years ago.
Yeah, I know.
I think, he's working on.
Can you send me his email address?
Oh yeah, I will. I'll send him.
I was just checking. Hua Xin Peng. I have his. I just checked.
Yeah. Hua Xin, because
I don't have any email addresses for colleagues at UST Beijing, but
UST.
I've been there many times, and it's sort of my.
Yeah, I think you definitely know him. I'll pass him his email.
Yeah, sure.
Yeah.
Thank you.
Yeah, I'm sure I think some people from USTB, because they heard of this seminar, I'm sure they're going to log in online. So yeah, at the moment nearly 82 people. Here, of course, everybody.沙刚，你要和Brian 说两句吗？
Hi, Brian.
Hi.
Say hello to Brian.
Nice to see you.
Yeah. Anyway, Shagang know about seminar. Shagang also advertise your.
Yeah, I'm in office to attend your lecture. It's a great pleasure.
Shagang also getting.
Okay.
Anyway,
remind me, where are you working now, Gang?
I'm in Shanghai. Nanjing University of Science and Technology.
Oh, I've been there many times. I like it.
Yeah. So next time you have a trip in China, welcome to come to Nanjing.
Well, I've been to Nanjing. I have an honorary doctorate from Nanjing University.
Yeah. Okay.
I have an honorary doctorate from NEU Shenyang as well.
Yeah, that's right.
英国人不是很严肃，所以呢，虽然他已经是院士，我们说话就像唠嗑似的，像在 pub 里唠嗑一样。那个沙刚老师也是他的学生。沙刚老师也是。
有个华新。
东大毕业生。
华新上来了。华新鹏。
大家坐吧，坐完一会儿到时间的时候开始介绍。
Okay, I think I switch my mic off.
Let me just say quickly that when I'm able to visit again China, I will do my best to come to Nanjing because it's one of my favorite places. I will do my best to come to Shenyang. Do my best to come to Zhejiang University in Hangzhou because those are three of my favorite places.
Yeah, that's great. We're looking forward to that.
I will try. So, Delian, can people see me on the screen? Is there a big screen there?
Yeah, Brian, will you share your computer screen so that we can see your PPT?
Yeah. Let me share. I'll do the share and then I'll switch on the PPT.
Play your PPT so that we can see whether this works. Yeah. 我把屏幕也录起来，将来存起来大家学的话，英语不太好的，看到什么词儿不认识记下点，然后回去以后像这种英语的这种 seminar 的，回去好好学习，提高英语啊！别弄得6级都不过，有的同学4级都不过，所以东北大学的毕业生不应该这样。Yeah, we can see the screen now. 华新，hello， 华新。I told Brian that, yeah.
Hey, Hua Xin, how are you?
Yeah, great to hear from you. To see you again.
And you're at Zhejiang now?
Yeah, I'm in Hangzhou.
Where?
Yeah, I'm in Zhejiang, in Zhejiang University.
At Hangzhou.
Yeah, in Hangzhou, yes.
Another of my favorite cities, by the wonderful lake, the West Lake, my favorite city.
Of course, you still our university guest professors.
Yeah,
that's right.
Yeah,
I am. So all three universities, Northeast Houston University, Shenyang, where Diliang is, and your university at Zhejiang University and Nanjing University, where Xiaogang is.
Yes.
I'm an honorary professor at all three, and it's great. When I
Yes.
can get to China,
Look,
I'd love to come visit you.
Yeah. Please do. Yeah, you have our standing invitation. Okay.
Good. Thank you so much.
Yeah, great.
How are we doing today? How many people are here?
Yeah, time.
We're already over 100 online now.
Oh.
那时间到没到？你们的表到没到？
124.
到了。Yeah, Brian, it's time up, so we're going to start now. Would you want to play the PPT so that I can see whether it's a move? Or you want to change to the second page? I can see the first page nicely.
Wait a minute.
I see.
Moving. Wait a minute.
Yeah, okay, good. You can turn back to the first page now. Yeah.
Okay. Good.
First, it works
Yeah,
fine. Okay, yeah, thanks. The system worked very well. Brian, I'm going to give an introduction of you, and then you'll start to give the lecture.
Okay.
Yeah. First, hello everyone. All the colleagues and students from School of Material Science and Engineering at Northeastern University in China, and also those friends online who log in online. Thank you very much for taking the interest to attend the, I think it's very important seminar in the field of material science research by Professor Brain Cantor from the Department of Materials at Oxford University, and also from the BCAST, Brunel University in UK. And I think many of you might know that Brain is my PhD or DPhil degree thesis supervisor. And also we are lifelong friends. So it's a great honor and a big pleasure for me to give introduction of Brain to you. So I'll just read from the Professor Brain Cantor is an emeritus professor in the Department of Materials at the University of Oxford, and a research professor in the Brunel Center for Advanced Solidification Technology at Brunel University. He's a fellow of Royal Academy of Engineering, UK, and also was previously Vice Chancellor of the University of York and Bradford University of UK. 第三个我用中文说一下，一个就是他们的工程院，皇家工程院院士，另外一个呢就是他们英国你要是直翻译的话叫副校长，实际上是英国的York 大学和Bradford 大学的校长，在Brain 当了15年的这个15、16年嘛，校长在York 大学当了10年，在Bradford 在当了5、6年的校长。现在呢，他已经这个退休了，就是相当于也不是退休，他其实没退休，在工作，现在又回到这个牛津大学。And also Brain is the head of mathematical and physical sciences at the University of Oxford, UK, and a research scientist and engineer at the General Electric Research Lab, USA, so many years ago. And of course, Brain has been, I think, first a lecturer, and then a reader, and then I think Cookson chair professor at the Department of Materials at Oxford for many years. And when Brain was working as the academic faculty member, I was studying there. That was in late 80s and early 90s in UK. And Professor Cantor's Brain's research has investigated the manufacture or the processing of materials, and has contributed to fundamental scientific advances as well as improvement in many industrial products. So in other words, it basically contributes to research on material science and also materials engineering. And he has supervised over 130 research students and postdoctoral researchers, and published over 300 papers and books with more than 10,000 citations. And his Google index is 50, and given hundreds of invited talks worldwide. and he's on the ISI list of most cited researchers. He invented the field of high entropy alloys and discovered the so-called Cantor alloy, and of course that's this topic. But on other that, of course, now as I mentioned to Brian, he's a star in this field, but he's also quite well known in work on metastable materials like rapid solidified materials, and obviously he's a student in the field of heterogeneous nucleation of solidification. So that means Brian has done quite a bit of work on the fundamental research on microstructure, microevolution transformations like solidification and solidification. He also did a lot of work on a lot of brilliant work on amorphous alloys and in early time. And he was awarded the Espenham Prize and the York Lifetime Achievement Award and the Rosenhan and Platinum Medals of the Institute of Materials. He's an honorary professor at our university, at Northeastern University, and also Zhejiang University, and the Nanjing University, I think Nanjing University for Science and Technology, and the Institute of Metal Research, the Jinzhou, in China. And he's also the honorary professor at the Indian Institute of Sciences, Bangalore in India. He's of course, as many of us know, he's one of the editors of the journal Progress in Material Science, and he was awarded the CBE for services for higher education in 2013. CBE 一个什么那个 honor 吧，那个爵士领。Okay, so Brian, it's a great honor for us to listen to your seminar today, and also after Brian gives the lecture, we're going to have a discussion of the topic of high entropy alloys, and after this, because we booked the session for 2 hours until Brian your time 11 o'clock, and also in China 6 o'clock in the afternoon, so we're going to have maybe half hour, 20 minutes for general sort of talk, which means anyone in the audience, online, or in this meeting room, if you want to ask a general question like, I'm a PhD student, how can I, graduate without any difficulties? Question like that, or I'm a young lecturer, I want to be superstar in 10 years later, what should I do? Something like that. Because Brian is he's not only the leader of the university, but also well known. I mean, within our research field, is quite well known scientist and scholar. So I think, and also we are good friends. So so I think we can ask any questions, informal questions to Brian. Brian, now I pass to you, and thanks. So now you can start your lecture. Yeah. You can hear me?
Good. Can you hear me? Can you hear me okay?
Yes, we can hear very well.
Good. And can you see my pointer if I need it?
Yes.
Can you see
we can see the pointer, very nice.
Okay, good. So look, thank you so much for Professor Zhang, De Liang, for inviting me to give this seminar. And as you have said, you've said some very nice things about me, which I thank you very much for as well. And you're right, we've been friends a long time. It's a great pleasure to be able to give a seminar to Northeastern University Shenyang, which was the first university that offered me an honorary professorship, although I now have several in China and in other places. So Shenyang is a little bit in my heart because of that. But so are many other parts of China, which I visited many times. So I won't go through them all, but I visited many. I must have been to China maybe 20 or 30 times. I can just say that I first went to China, first came to you in China in 1993, which was a long time ago, and China was very different in those days. I remember going out the first day. I stayed at UST Beijing, University of Science and Technology in Beijing, and I stayed in a dormitory room on the campus. And I went out for a walk that evening, the first evening I was in China. And I went across the road, and there were about 5 million bicycles with people on bicycles. There were not many cars in those days, but there was a lot of bicycles. I was frightened to cross the road because I thought I would be knocked down by the bicycles. So I've seen China develop tremendously, and it's been a great pleasure to see that. And I've had some wonderful Chinese colleagues. As soon as this pandemic here in Europe dies down like it's died down in China, I look forward to visiting again. Anyway, my talk is about multi-component high entropy alloys. And as Diliang has said, as it shows here, I'm a professor in the Department of Materials, emeritus professor at Oxford University. I'm in the materials department, and I'm a research professor at BCAST, which is a big research institute at Brunel University in London. And that's a big academic industrial linked research lab working on applied research with many companies. There's about 150 people in that research institute. And our big project, we were just funded by the government, is on sustainability of materials. And so that's a very big project, which I am now helping to coordinate to try and get rid of all the mining of metals over the next 20 or 30 years, because you may not know this, but metals and the metals consuming industries, things like construction metals, construction industries, packaging industries, transport industries, aerospace, automotive, all those industries collectively can make up about 15% of all greenhouse gases and all pollution and all energy use. So we've got to stop the mining of metals. There's enough metals in circulation that we don't really need to mine anymore. Not the main ones, not the big ones, some of the special ones we do. But we've got to find a way of recycling everything much better. So that's our biggest project that I'm working on. But at Oxford, I do more fundamental work. And one of my fundamental bits of work is multi-component high entropy alloys. And that's what I'm going to talk about. So let me get going. Oh. Moving forward. Oh, there we go. So I have three take-home messages, which I want you to know at the end. The first one is that human history is the history of materials, the history of the development of new materials. All the history of the development of human beings and people is about the development of new materials. Materials are absolutely crucial to every single step, and I will explain that to you in a minute. The second thing, which I want you to know, is that all materials are alloys. We don't use pure materials, pure components, as we call them. What does that alloys mean? It means that we make materials from other materials, which we call components, pure materials, pure components. And we don't use pure components pretty much, apart from occasionally decoratively, and even they're not usually very pure. So all materials in the real world are alloys. They're mixtures of other materials, starting materials or components. And we'll see this. So human history is not only the history of new materials, it's the history of new alloys, new mixtures of materials. Third thing I want you to know is that there are gazillions of materials. That's not a technical description. Gazillions is a slang way of saying a lot. I'll be a bit more accurate about it later in my talk. So those are the three things I want you to go away knowing and understanding. Oh. So here's my brief history of materials and the world. So if we start 3 million years ago, 3 million years ago is the beginning of the Ice Age. It's easy to remember, 3 million years ago, the beginning of the Ice Age. It's also when humans first appeared. Humans evolved from apes, from Australopithecus, which is the same, which is a fancy word for southern apes, 3 million years ago at the beginning of the Ice Age. It's also the beginning of the Stone Age. These three things are linked. Because the weather got worse because of the beginning of the Ice Age, it became advantageous for apes. Apes wander around in small groups, family groups, and it became advantageous for them to develop improved brain capacity so that they could start to use stones as tools. It was much harder to get food, so to be able to use stones as tools was the key thing. And so humans emerged and evolved in order to develop tools so that they could do better in the Ice Age. It all happened 3 million years ago. And of course, the material that drove that was flints and stones, which they found. So these are not manufactured materials. Well, they are manufactured because they made them into tools, but they basically found them. But what are flints and stones that you make into tools? Well, they're alloys. They're oxide alloys. All the materials in the world we see around us, the rocks and the stones and the sand and the clay and the soil in the world outside, geological materials are basically alloys of oxide. Everything is oxides. Why is everything oxides? It's because there's a lot of oxygen in the atmosphere. So everything is oxides, and some oxides are useful, some mixtures of oxides to make tools. Some of the ones you can find. Flints and stones you can find on the ground and you can shape them. And they're basically made out of silicon oxide with little bits of aluminium oxide, calcium oxide, and iron oxide, which are very important because they allow the flints and stones to be fractured in a way which allows you to make tools from them. So that's the first big development, and it's driven by a development of a new material, a new alloy. So we jump forward. Now, most of the time since the beginning of the Ice Age, 3 million years ago, more than 99.5% of the time since 3 million years ago was the Ice Age. Human beings have mostly lived during the Ice Age, a bit like apes, going around, cutting down plants and eating from trees and hunting animals in pretty poor weather. But the end of the Ice Age occurs about 12,000 years ago. That's 99.6 or 99.7% of the time since the beginning of the Ice Age. So very, very recently, 12,000 years ago, 10,000 BC, we come to the end of the Ice Age. Now, the end of the Ice Age is also the end of the early Stone Age, the Paleolithic, and the beginning of the Neolithic, the New Stone Age. And the reason, but it's also an even more important point, it's what's called the agricultural revolution. The biggest revolution in human existence is often said to be the agricultural revolution, which occurred 12,000 years ago at the end of the Ice Age and the transition into the New Stone Age. So these are all linked again. And the difference was that because the Ice Age went away, what's often said is that because the Ice Age went away, human beings, instead of wandering around as what are called hunter-gatherers and finding their food just by going around and finding plants and finding and hunting animals, they began to settle down in houses and in small villages and in bigger groups. And they started to farm, and they started to domesticate the plants, and they started to domesticate the animals. This is when we start to have grain domesticated in the near the Mediterranean, in the Middle East, and we started to have rice domesticated in the Far East, in China, and we start to have maize domesticated in the Americas. So domestication of plants starts to happen, and domestication of animals. Initially, chickens in China and sheep in the Middle East. So domestication of plants and animals. So the food was now being farmed. Now, and people began to live in villages. It was a massive change in how people lived. It was driven again by materials. It's not often said. It's because of the development of clays. Now, what are clays? Clays and bricks. They're again oxide alloys. They're aluminosilicate alloys. They're mixtures of clay and soil and sand that's found just in the earth. But if you heat it up, it's a mixture of alumina, aluminium oxide, silica, silicon oxide, and water. And if you heat it up, the water vapor is evaporated, and it bonds together to make a very useful material. So people learned towards the end of the Ice Age how to do that. And that is why you could have villages, because you had better materials to build houses, and you had also clays which could make pots to store the food. If you couldn't store the food, there was no point domesticating the animals and the plants. So at the base, the material development of clay pottery, by using fires and kilns to heat clays and soils to create bricks and clay pots is at the heart of the agricultural revolution and at the end of the Ice Age. Now we jump forward another 6,000 years and we come to the Bronze Age. People would by then, for thousands of years, had been making their clay pots. They were living in farming communities, and they must have been very surprised at some point, because at some point they will have had a fire, a kiln to make some clay or bricks, and they would have had it on a particular ore which contained, let's say, some tin oxide or some lead oxide or some copper oxide, and the copper in the wood will smelt the copper oxide and turn it into copper, or the tin oxide and turn it into tin. So initially they would have been amazed to see shiny metal at the bottom of their fire, which they used, and their kiln, just oozing out. Now at first that was not useful. It was used decoratively, because pure metals like tin and copper and lead, low melting point metals, which are quite easy to smelt in a fire, in an open fire, and at first they're very soft. They're pure. They're not very useful, but they were used for decorative purposes. But about 6,000 years ago, about 4,000 BC, about 6,000 years after the agricultural revolution and the end of the Ice Age, people discovered if you take some of the tin and you mix it with the copper, you get, or more accurately, you take copper and you mix a little bit of tin into it, you get bronze, and you get a really good material. It's not soft like pure copper or pure tin. It's a hard material, because the copper, the soft, moldable, formable, castable copper can now be made hard because of the copper-tin compound, intermetallic compound, which precipitates CuSN4 and gives the hardness. So that was the Bronze Age. This had a massive impact on the world again, and suddenly you get the growth of big cities. You get the growth of empires. The Bronze Age is what drove the Egyptian Empire in the Middle East. The Shang dynasty in China, which is one of the earliest dynasty, began because of the Bronze Age. The Mayan civilization in the Americas. A whole series of big civilizations and famous dynasties grew up because of the Bronze Age. So, and you could make better tools out of bronze than you could out of flints. We jump forward another few thousand years, and about 1500 BC, about 3,500 years ago, in the Middle East, people had another surprising discovery. They discovered how to make irons. What happened is, iron is much more difficult to smelt because it has a high melting point. So if you smelt on an iron ore, you will form iron, but you don't. Unless the iron melts, it doesn't separate from the oxide and the soil and the gangue and all the other stuff that's in the base of the fire. Now people began to make bigger and better fires. Basically, they learned how to make chimneys. And if you put a chimney on a fire, the fire gets hotter, and you then find that you can make iron by smelting as well. The carbon in the wood, again, will reduce the iron oxides into iron, but iron is different to copper or tin or lead. It dissolves quite a lot of carbon, a few percent, not a massive amount, but it dissolves a few percent of carbon, and that produces what we call ions. By peculiar terminology, ions are not very pure iron. They're irons, wrought iron and cast iron, are iron with a few percent of carbon in them, because that's what you get when you smelt iron initially. And that's what people discovered at the beginning of the Iron Age, about 1500 BC. And this was discovered by the Hittites in the in the sort of an area that's near Turkey and Anatolia now. And that led rapidly to the fall of all these famous civilizations, the Egyptian civilization, and the growth of new civilizations who learned how to use the irons because they produced much better tools. The iron carbon alloys were better than the copper tin alloys. And it's when, by the way, China began. As China, the Qin dynasty begins just at this point to do with the Iron Age. So that's how why we have the Iron Age. And of course, the Roman Empire is based upon the Iron Age. The Romans took over from the Greeks in the Middle and Near East because of their use of the of iron, wrought iron, and in China it was more cast iron. So we're going to jump forward again to the. So I'm going to show you some pictures first of all. I don't know why the slides are moving rather slowly. Oh, there it is. So there is a flint tool from 2 million years ago, and there is a bronze dagger from about 1500 years ago. There is a copper smelting hearth. This would have been an early copper smelting hearth from Israel to make copper and then bronze. And you can see it just looks like a fire that you might make if you're out camping. And here is a picture of an early Iron Age kiln for making for smelting iron. So you put a chimney on the fire now, and that makes it hotter. And here's the smith, the smelting smith, who is feeding the fire here, and out of here will be taken the iron. And here's the blacksmith who's going to hammer it into a useful material. So we jump forward again to the second biggest change in human existence after the agricultural revolution at the end of the early Stone Age, at the end of the Ice Age. The second big, after the agricultural revolution, is the Industrial Revolution in the 18th and 19th centuries. And this relied also, this of course is the development of machinery, of the development of engines, the development of mills for making manufacturing processes, of textile mills, of printing presses, of power stations, of electricity distribution, of dynamos and transformers, of transport revolution and the ability to make engines and to make trains and then to make cars and aeroplanes. All of this, and of course, and all of this depended upon, again, a material development, the development of steels. Steels are a purer form of iron carbon than irons. Irons, wrought iron and cast iron, which have been used from the beginning of the Iron Age through to the 18th and 19th centuries, that were iron with a few % of carbon in, which makes a strong material, much better than bronze, but it's not very formable. And the revolution was the understanding with steels of how to then refine the iron by converting it into steel, by reoxidizing some of the carbon out of it to get the carbon levels down to between 0.1 and 0.8% carbon. Most of you are material scientists, you will know this. And 0.1 to 0.8% carbon is a steel. And because it's much more controlled amount of carbon, we can then tune the softness and the formability and the ductility, which is important to be able to make things, together with the strength by modifying exactly how much carbon and how much other alloying elements we add to make it strong, but also its resistance to fracture from that residual softness. So we can tune all of that. And without that, we could not have had the Industrial Revolution and all the wonderful things that we now take for granted. Of course, the Industrial Revolution in the 18th, 19th century was in Europe, and in China and India, it's happened much more recently. But it's had a massive impact on so many people's lives and made them so much better. Jet engines developed in the mid-20th century. Air transport was not possible without another alloy, nickel superalloys. The story of jet engines is very interesting. Frank Whittle was the man who first proposed the idea of a jet engine instead of a reciprocating engine like we use for cars, which were used in the early aeroplanes. And he proposed it in 1929 to the Ministry of Defense in Britain. And it was turned down. It was actually turned down by another famous material scientist, Griffith, who invented fracture theory. Griffith was in the MOD, and he looked at it and he said, it'll never work. It'll never fly, jet engines, because the temperature which will be generated in the middle of a jet engine is too hot. We don't have any materials which can cope with it. And he was right. He was right about how hot it was getting, but he was wrong about whether we had materials to cope. Well, we didn't have materials then, but the very same year, 1929, that he rejected Whittle's suggestion, Bradley, Pilling and Merica, working for International Nickel Company, patented the patent which developed nickel superalloys. The idea that if you add some small amount of aluminium to nickel, you can have a much higher temperature metallurgical material which can be used at the heart of a jet engine. Because of that rejection, it took another 20 years before jet engines were developed after the end of the Second World War. And then finally we jumped, but it all depended upon the development of an alloy which could cope with the high temperatures. Then we jump to our present time, and we're going through the third biggest revolution in humankind's existence, in humans' existence, the information revolution. We know about that. We're in the middle of it. We don't know the full extent of it yet, but it's all to do with computers and the internet and telecommunications and artificial intelligence and all the things which are being developed right now. And it all depends, of course, on alloys. Silicon chips are what are at the heart of it. We can't have information revolution without silicon chips. And silicon chips are based upon silicon alloys. They're microalloys. We say they're doped. It means a microalloy, silicon with a small amount of aluminium or boron or phosphorus or nitrogen to give it its special semiconducting properties, which allows the development of these information handling chips. So everything in our development has depended on the development of materials. Let me see if I can go now to my next slide. Oh, here it is. So this is some pictures of the developments, the later developments. So on the Iron Age, you can see this is Damascus steel knives. These are ones at the top end of the steel hierarchy with about 0.8% carbon. So they consist of two phases, iron and cementite, the hardening cementite phase, Fe3C, with the soft iron, which allows them to be made into these shapes. If you go to the low end, then the shapeability becomes higher, but you can still get the strength. And at low carbon steels, you can mold beautiful things like these beautiful cars, like the Golden Era Cadillac here. The jet engine here, this is a man, I don't know who he is, but this is a GE90 engine. I worked for GE in about 30 or 40 years ago, and the GE90 engine was developed towards the end of the 90s. This is the biggest engine in the world. It's used to power the 787 Dreamliner. And of course, the way it works is these blades here, these ones are not made out of nickel superalloys. It's not hot here. The air is quite cold and comes in here. These rotate, suck the air in, the air gets compressed, the fuel is burnt, the air gets faster and faster, the fuel gets burnt, and it shoots out the back end, which is what causes the jet engine to go forwards. But before it does that, it hits the turbine, another row of blades like this, which are rotating. And it's those blades which are connected by a shaft to these blades, which help suck the air in the first place. That's how a turbine works. And the blades at the back end here, the turbine blades, which are hit by the hot rush of air, have a melting point, which is actually 200 degrees below the hottest melting point, the hottest temperature of the air by the time it's been compressed and the fuel has been burned. So it's one of the wonders of the modern world. But the metal, the nickel superalloy, looks a bit like this. It consists of a background of nickel with a hardening phase of nickel aluminide, which are these square blobs here. And that's how a superalloy works. And everything depends, as I said, on alloys. I don't know why my slides are so slow to move forward. I apologize for this. There we go. And here's the silicon chips. You have to grow a big silicon crystal piece of silicon single crystal. This is a 200 millimeter diameter single crystal. In my PhD, I grew single crystals which are just a few inches long. It's not easy, and it's certainly not easy to do it this big. And nowadays they make 400, even 600 millimeter diameter single crystals. They take thin slices on them. They're incredibly pure, parts per million purity. They take thin slices like this. And this is a single crystal wafer. I just picked this up from the internet. You can buy this slice of one of these for $40. And it's got on it hundreds of individual silicon chips. And each silicon chip is a microprocessor or something like that. It's a fantastic technology, and just how cheap it is remarkable. So each of these is a silicon chip. Each of these small squares will have on it literally thousands of individual silicon transistors or diodes or individual components. And here's a picture of one of them. and I'm not going to the details, but this distance here is about 10 atoms, and each of these regions here has got different amounts of doping of, as I said, phosphorus and boron and so on, of the silicon, to give all the functional properties. It's a remarkable technology. But the key point I want you to know is that the technology all depends upon materials. So everything in human existence that's been developed depends upon materials. So I hope I persuaded you that humankind, the history of humankind, is the history of the development of new materials and alloys, and that all materials are alloys. They're mixtures of other materials. So those are the first 2 points I wanted to. Now I'm going to go on to talk about multi-component alloys, which are the new alloys. So all of this existence, ever since 3 million years ago, all of these alloys have been developed using what I call conventional alloying strategy. We didn't consciously do it this way. It's just evolved this way, very natural, very understandable. We tend to have one major component for the main property, and then we add a second material for the any secondary property, and a third material at small levels usually, just to tweak up the secondary properties, the secondary and tertiary properties, the second and third properties. And that's what happens. So nickel superalloys, for instance, are basically nickel because it's a high melting point metal, and it can be formed into those funny shaped blades, those aerodynamic blades. But it wasn't good enough until it was strong enough. So you have to add a certain amount of aluminium to make it strong enough. And you have to add a little bit of chromium to make it corrosion resistant. So that's typically what happens. But it's not just metals, it's also ceramics. You know, if you want window glass, it's silicon oxide, because silicon oxide is transparent if it's cooled reasonably rapidly from the melt. But you add actually sodium oxide because that lowers the melting point and makes it form glass a little bit more easily. And you add other oxides to give it strength. So this is true of every single material that we use. It's one major component with a few additions of a few extra small pinches of things to give secondary and tertiary properties. So in the late 1970s, 78, 79, I began to go around saying to people, why don't we have a multi-component alloying strategy? Why don't we ever mix large numbers of components in equal or near equal proportions? Why don't we take sometimes 4, 5, 6, occasionally we do have, usually we only have 1 or 2. Bronze is copper with a bit of tin, occasionally is a third element. Most steels are iron with carbon and maybe a little bit of manganese, tiny little bits of carbon and manganese. But occasionally we have a lot more components, but they're in tiny little pinches. So why do we never mix 4, 5, 6, 7, 8, 9, even more components in large proportions? Why do we never have 10, 20, 30% of 6, 7, 8 components? I began to ask this question. I'll tell you what the answer was in a minute, but let me just explain a bit more by going to the next slide. I don't know why it doesn't go. There it is. So if we have a ternary system, we can imagine each point in this triangle is that we can imagine this is nickel, aluminium, and chromium at the corners, and each point in here is a nickel, aluminium, chromium, different composition. So our nickel superalloys are nickel mainly, with a bit of aluminium and a bit of chromium, and maybe a bit of something else. So they're in this region. If we have silicon, if we have our window glass, it's silicon oxide here with a little bit of sodium oxide, maybe a little bit of aluminium oxide, and it's down in this corner here. So all of our materials are at the corners or along the edges or near the corners of phase space. In a ternary system like this, and a quaternary like this. In the central region, we don't ever make these materials. We've mostly never investigated them. We've never made these, and once we get to quaternary ones, we've never even made them. There's just literally thousands. If you imagine going to 5 component or 6 component or 7 component materials, well, there's just literally millions and millions of materials in the middle here that we've never ever made. And I began to ask the question, why do we never do that? And I'll tell you what the answer was. People said it's a crazy idea. They said, you're crazy, Brian. Why would we do that? No, nobody would do that. We've not been doing that for years. We're not going to start doing it. And the problem I had was that my scientific colleagues said it was an interesting idea, but they thought it was a bit crazy. my research funders said, well, this is crazy. This really is a crazy idea. We're not going to give you any money to study it. And even research students and research postdocs who I wanted to have working with me said, we don't want to work on that. We want to work on some hot topic. Somebody's making a noise there. We want to work on some hot topics which we can get jobs, so we can get a job when we finished our studentship or our postdoc with you. So I struggled to get anybody to do any work on this or to make any progress. But finally, I persuaded a young man called Alan Vincent, who was a student at Sussex University, where I was a lecturer initially. I persuaded him to do his undergraduate project. He was just an undergraduate. He did a 50-hour project, and I persuaded him to try. He was a feckless young man. He was not too interested in science, and he agreed to do this. So we made up this material here. This is 20 components with 5% each, and it was until about 3 or 4 years ago, maybe about 2 years ago, the world record for the most components ever made in an alloy. 20 components. I've seen recently in the last year or two 22 and 24 component alloys, but this was the highest since 1980, which is when we made it, 1979, 1980. So it's the highest for pretty much 40 years. And I made this actually, but then Alan did his project and he looked at it and it was a mess. You can see it was very brittle. It wasn't had lots of phases in it. The X-ray diffraction traces were complicated. It had lots of different phases, and it was a bit of a mess. And we weren't quite sure what to do next. But then we noticed that this background phase here consisted of just 5 components: chromium, manganese, iron, cobalt, and nickel. The first 5 here, in equal proportions. We noticed that in a scanning electron microscope when we did energy dispersive X-ray backscattering, and that was very surprising. In fact, that material is what Alan then began to look at. Come on.
没事，我在这儿摸吧，没事。
Well, there it is. I don't know why it's so slow. I apologize. So that material is the Cantor alloy, as it says up here. The Cantor alloy, which consists of chromium, manganese, iron, cobalt, and nickel in equal proportions, 20% each. And it turned out to be single phase, face-centered cubic. And this was a big surprise. And of those 5 components, only 1 is face-centered cubic at room temperature, nickel. The others are not. Many of our metals are face-centered cubic. Here's a face-centered cubic structure. Copper, pure gold, pure lead, pure aluminium are all face-centered cubic. And it's the face-centered cubic structure that gives the softness and formability that led to the Bronze Age and the Iron Age being developed. It was the formability. We've got plenty of hard and strong materials, but then most of them are brittle and they fracture, and we can't form them into materials, and we can't prevent them fracturing. It's the face-centered cubic structure that makes that work in most, sometimes body-centered cubic, but it's because the atoms can slide over each other and the defects can move around in this structure. But, you know, if you add tin to copper, what happens is, you know, if this is all pure copper, each of these atoms is copper, then up to about 1% tin dissolves, and 1 in 100 of these atoms is tin. But beyond that, it forms a compound because of the chemical attraction of the copper and the tin. If you do the same with iron, and you add face-centered cubic iron, and you add carbon, beyond some point, the carbon forms iron, Siemens carbide. If you have nickel and you add aluminium, you get 0.1% of aluminium will dissolve in roughly in nickel, 1 in 1,000 atoms, and then beyond a certain amount, you get nickel aluminide, which is the strengthening phase I showed you. So that's the basis of all of our metallurgical and our ceramic materials, is manipulating that kind of thing. But you do not expect to have 5 components in equal proportions, so on a single face-centered cubic lattice like this. That means that 1 in 5 of every atom at random is chromium, manganese, iron, cobalt, or nickel. And this is now called the Cantor alloy, and it was a big surprise. And in fact, there's a massive range of alloys around this particular composition. But let me continue with the story, because Alan did this work. He published his, he did his dissertation, he got his degree, but the research wasn't good enough to publish. Now, as it happens, that was when I went off to GE to work in the States, and I came back to Oxford, but I came back full of interest in applied science. And I stopped trying too hard to work on this. And anyway, I still couldn't get anyone to work on it. Nobody was interested. And we hadn't been able to publish it because the research had not been done well enough. The micrographs were not good enough. And so nothing happened until 1998. Nothing happened for about 20 years. And then I persuaded another student, undergraduate, Peter Knight, while I was at Oxford, to repeat the work. Peter repeated the work and demonstrated it was right. And he went off, got his degree, did his dissertation. But once again, the research was not good enough. The micrographs were not good enough. The X-ray traces were not good enough for us to be able to publish the results. So I turned to a postdoc working with me at that time. Liang will remember him very well, Isaac Chang. He was from Hong Kong. He'd moved to Britain when he was quite young, when he was about 5 or 6 or 7 years old, and grown up in London. He'd worked with me for about 5 or 10 years. He was a research student about the same time as Liang, and he stayed on with me like Liang did as a postdoc. And I turned to Isaac and I said, look, please do this work and repeat it again and do it properly. So Isaac did a beautiful job. And here is some of his pictures. This is the as-cast Cantor alloy. Chromium, manganese, iron, cobalt, nickel. There's another picture on the next micrograph, if I can bring it up. There it is. And if you, it's soft. It's like all face-centered cubic materials. If you can forge it or you can roll it and deform it, and then recrystallize it by heating, and you get nice equiax microstructures like this. It looks exactly like the pictures before with dendritic structures from the casting, and which is what you would get with copper or gold or aluminium, pure aluminium. But when you recrystallize it, as you would do with copper or gold aluminium, you get equiax microstructures like this, with the occasional annealing twin. But the unusual feature, it turns out, is that it's got very high strength. So face-centered cubic copper or gold or aluminium has a strength no higher than about 100 megapascals, and then a lot of ductility. And we work very hard to make it have higher strength, but that always restricts the ductility. Because this is face-centered cubic, the ductility is still 50 to 100%. Initially, it's very, very high strength. That's why people recently have become very, very interested in this material. And in fact, if we plot an Ashby map, and of course you can make it stronger still by doing the same sorts of things as you do to high-strength steels or high-strength aluminium alloys. You can add other components, and you can play with the composition. So this is why people are interested in this material, the Cantor alloys, because if you plot it on an Ashby map of fracture toughness against yield strength, down at the bottom here, you can see polymers and glasses and ceramics. They're not very tough because they fracture easily. Pure metal down at this end here, pure steel, pure iron, pure aluminium, and they're much more resistant to fracture, but they're also not as strong as the strong ceramics. But if you then use our metallurgical development technique, we can push their strength up like this to get high strength steels, high strength nickel alloys, and so on. But here are the high entropy alloys, including the Cantor alloys, the multi-component alloys. They've got the best combination of fracture toughness and yield strength of any materials that have yet been developed. Sorry, I'm trying to move to the next slide again. You have to bear with me. I don't know why. It seems to take some time to move. There it is. So we published our paper in 2004. The work was done in 1998. Isaac redid the work and we presented at a conference in 2002 and we published it in 2004. And nobody took any notice for just the same reason as before. There was a second paper published on it in 2004. The two first papers had 8 citations in the first 2 or 3 years. Now we're getting thousands of citations every year to those two papers. And not only is there one Cantor alloy, there are literally hundreds and thousands of Cantor alloys with different compositions. The book in 2014 by Murthy, Ye and Ranganathan, Jinwei Ye was the other person who developed this idea independently of me in the 1990s and also published in 2004. Murthy, Ye and Ranganathan's book in 2014 lists 3 pages of different Cantor alloys, all single-phase fence-centered cubic. In the middle of multi-component phase space, there are literally hundreds of face-centered cubic alloys. The Murthy, Ye and Ranganathan have just produced the second edition of their book 2 years ago in 2019, and there are 4 times as many of these alloys. Too many for me to show you, so I haven't bothered showing them. An enormous region in the middle of multi-component phase space consisting of single-phase FCC alloys. We've been studying quite a lot now, but we've still only studied a few examples. I'm still struggling to get onto my next slide. Please, come on. So Miracle and Senkov, Dan Miracle is the head of the Air Force Research Labs in the US in Ohio, and his colleague Oleg Senkov, who is a Russian who works with him, published a very influential review in 2017, and he pointed out that these multi-component alloys, we have developed, he said, and they're shown here, I won't go through them all, 8 different new categories of materials. The Cantor alloys, the face-centered cubic ones, are only one category. We've got a body-centered cubic category, we've got a HCP category, we've got a rock salt based category. There's 8 different categories of new materials which are being studied. And he said, we've only just started, we've only just scratched the surface. So I hope I've explained to you that there are literally millions of new materials to be discovered because of this multi-component alloy concept. So let's look at it in a little bit more detail. How many materials actually are there? Could we make? How many materials could we possibly make? Well, think about the system with C components. Imagine that we've got C starting materials to start with and we can mix them up. And let's assume that we treat a material as different if it differs by X%. So, you know, if we change the composition of one of the components by 1% or 0.1% or 0.01%, we've moved to a different material. In other words, there are 100 over X composition values for each component. What that means is, if you think of that ternary alloy that I showed you before, it means that if you change the composition, the number of points with the different materials in that ternary triangle are all separated by N. And that's the number of points you've got in that triangle. Well, the total number of alloys and materials, if you have C components and the materials differ by X%, there's N 100 over X composition values for each component. The total number of alloys and materials, big N, is given by the law of combinations of repetition, which is a complicated bit of, very simple bit of schoolboy or first degree maths, combinatorial maths. And the answer is this, it's this formula here. So I won't bore you with the details, but that's the answer. So knowing the answer, now we need to work out what the actual number is. So how many components can we have? Well, there's 120 different elements. So really, we could probably use 120, we could say. But of course, many of those are toxic or radioactive or only last for a millisecond or less. So the real usable number is more like 80 or 90. So we could probably say C was 80, to be perfectly honest, and that would be very reasonable. But let's be really conservative. And let's just stick to the main metals and the main semi-metals. Let's leave out fluorine and iodine, and or even though fluorides and iodides are important materials, let's leave out some of the things like oxygen and sulfur, because they're usually more like impurity materials. But even so, we've still got 60 materials we can mix together. 60 elements. And X, now how big is X? Well, we normally specify materials to about at least 0.1% and sometimes 0.01%. If you look at the composition of a steel or a ceramic, that's the specification. A very poor quality metallurgical or ceramic material is 1%, specified for 1%. And of course, some materials like high strength steels or silicon or nickel superalloys is specified to parts per million. So again, conservatively, let's say take X as 0.1%. In that case, that formula gives you the answer of 10 to the 100. The total number of alloys, if we have 60 starting materials and we can change their compositions, the composition of each of those components by 0.1%, the number of materials is 10 to the 100, which is a Google. And for comparison, I think this is an allowed Google in China. For comparison, there are 10 to 66 atoms in the galaxy and 10 to the 80 atoms in the universe. This means that there are more materials than there are atoms in the universe. And if we think that the total number of known materials is approximately 10 to the 12, about 1 trillion, it's a minuscule fraction. So this is my explanation of the word gazillion. There are literally gazillions of materials, far too many for us to have ever looked at. And even though we've been now looking at multi-component materials, we've still only scratched the surface. Here's the 10 to the 100 for 60 components and 0.1 for X. But if we probably 80 or 0.01 would be more reasonable, and then we'd have 10 to the 200 materials. So it's an amazing thing. Now, I'm going to go on to a different set of issues now. I'm going to look at the material structure in the Cantor alloys, the FCC alloys, and in the solid solutions that are seen. There's a lot of these solid solutions. There's this whole patch area of phase-centered cubic material in the middle of multi-component phase space. But there's also a massive, by the way, the Cantor alloys, there are literally millions of Cantor alloys, millions of FCC alloys in a great big patch in multi-component phase space. There's also millions of BCC alloys nearer the early transition metals, based on the early transition metals. There's another region of borides, actually mixed carbo-nitro-boride, rock salt structure, a massive region of different, with many different millions of different materials. And we've only begun to look at them. And they're separated by regions where there's more than one phase, where there's multiple phases. And so that's what the structure of multi-component phase space looks like. Now I'm going to talk about the regions where there are solid solutions, more like the Cantor alloy. So here's the 5-component Cantor alloy. I didn't draw these. It's not drawn very well, but there are 5 components. There are A, B, C, D, and E. And here is a 10-component system drawn. They're all drawn from this book. And this is drawn slightly better because, of course, these atoms are not all the same size. So the Cantor alloy has 5 components, but there's nothing to stop us thinking about possibly 10 components. But you could get the idea. These are drawn on a square lattice, which is not a realistic lattice. But the point I want you to see is this. Of course, there are different atoms at the different points in the lattice. We've got A atoms, we've got B atoms, we've got D atoms. A atoms, and in the 10 component, we've got J atoms, we've got H atoms. But it's more complicated than that, because the properties of an A atom depend upon its surrounding atoms, because it's affected by them. So this A atom is surrounded by, you can see, F, E, B, C, H, F, C, B. But this A atom is surrounded by a different set. Every A atom is surrounded by a different group. So the local structure varies from every single point, not just because we got 5 components or 10 components, but because of the surrounding atoms, the near neighbors of each initial atom. Now, that is a remarkable thing, because if you have FCC copper, or pure gold, or pure nickel, every point is exactly the same. And even if you have a solution, like you add a little bit of aluminium into nickel, even if you add a little bit of carbon into iron, even if you add a little bit of tin into copper, only the occasional atom is different. So most of the atoms are the same. In this case, we've got a massive number of different local structures, partly because there's different atoms there's different atoms A, B, C, D, E, F, and so on. but even every single A atom is different. How many different local environments are there? Well, if we take the Cantor alloy with 5 components on FCC, where there are 12 near neighbors, so a local cluster is 13 atoms. How many different 13 atom clusters are there if you have 5 components? I tell you the answer, it's 20 trillion. It's a very big number, 20 trillion. It's so big that if you want to have an average of the material, to have an average material, you need to extend the material enough to encompass all different local structures. And to do that, you need to have a piece of material which is several microns in dimension. So if the grain size is smaller than about 20 microns, each grain of the material will be different if the crystal size is smaller than about 20 microns. That's for the Cantor alloy. By the way, if you go to 6 components, it's more like 200 trillion. And you need a piece of material of 100 microns in size to have an average block of material, to average over all the different local environments. And by the way, if you think about it, an atom like A is not only influenced by its near neighbors, it's sometimes influenced by its second near neighbors. If you include the second near neighbors, then it goes off the roof. It turns out that in the 5-component face-centered cubic Cantor alloy, then, and if you include second near neighbors, and some properties depend on second near neighbors, there's about a 4 or 5% effect of second near neighbors, which is sometimes crucial. Then the number of different local clusters you can have turns out to be, again, it gets to 10 to the 20 or something like that. And you need to have a piece of material several meters in size in order to have an average material. So every single piece of material you would make of that material for that particular property will have a different property because you won't average over the range. So that's one of the most fundamental things about these multi-component high entropy. Now these are called high entropy systems. I'm going to talk about this structure now about a number of particular sort of properties. I'm going to say a bit about disorder and entropy and the heat of mixing, the thermodynamics, because of course they're often called high entropy alloys. Jinwei Ye invented the name high entropy alloys, and that's what they're mostly known as. And I use that term a lot. And the alloys that are in the middle of this face-centered cubic region or the body-centered cubic region are high entropy alloys. The multi-phase materials are probably not high entropy. There's been some confusion about this, but in between those, there are still low entropy materials. But within these big solid solution regions, they are high entropy. And I'm going to talk about that little balance, you know, when is it high entropy and when isn't it? I'm also going to say a little bit about lattice strain because of these different atoms are all different sizes as shown here. And because these local environments are different, the lattice is locally strained. It's expanded or squeezed, depending on whether you've got a big atom like C or a little atom like A. So there's an enormous kind of lattice strain, which varies from point to point. I'll say a little bit about that, and I'll say a bit about how that influences the diffusion, that's the atomic motion inside the material, and the slip, that's the way that the atoms slide over each other to be formable and prevent fracture. And then I'll say almost nothing about these other things at the end. So it's frozen again. We'll have to just wait a second until I can get to, there we go. So here's binary solution thermodynamics. I don't want to bore you with too much maths, but you should understand this. The free energy is the sum of the chemical potential for a composition XA and XB. The binary material is the sum of the chemical potentials of the materials before the A and the B before you mix them, plus a free energy of mixing. The free energy of mixing depends on the enthalpy of mixing and the entropy of mixing. If it's ideal, there is no enthalpy of mixing, and the only entropy of mixing is the random distribution of the A and the B atoms, and that's got that entropy there. So that's the core of the entropy that we're going to be interested in. Now, most materials aren't ideal. There is some enthalpy of mixing, so a regular solution, the enthalpy of mixing is not very large, so the entropy is still this, it's the same. And if we have a more realistic quasi-crystalline or other, then there's the enthalpy of mixing, it gets more complicated. We still got this configuration entropy of mixing, and there's some additional entropy terms. But all we need to think about is there's enthalpy of mixing, and there's some configurational entropy. We don't need to worry about what's called the excess entropy too much. If we go to, come on, if we go to multi-component solutions, it's not very different. Free energy, we have to do a summation now over all the different components. So these become sums, but otherwise the structure is pretty much the same. There's an enthalpy of mixing and an entropy of mixing. The entropy of mixing is the random one here, the ideal one or the regular one. There's an enthalpy of mixing, an entropy of mixing, and an excess entropy. But we're interested in this configuration entropy because we've got a large number of components. And how does it compare to the enthalpy? So this is the entropy. It goes up as you increase the number of components. It goes up not too fast, but if you get up to 5 components, the entropy in joules per K per mole is about 14 actually. It's about 15 at 5. Well, sorry, it's 15 at 6 components. At 5 components is about 14 joules per K per mole. And if you turn that into free energy at 1,000 degrees, it's about the same number, 14 or 15 kilojoules per mole at 1,000 degrees. So that's where we are. If we have more components, we can get up to 20 or even 25 maybe, but you need an awful lot of components to get that far. Come on. And these are the enthalpies of mixing for the Cantor alloys. Now the Cantor alloy, the individual binary enthalpies of mixing are given here, and you'll see that they're not very high. The highest one is manganese nickel, which is 14. So that counteracts, that is just okay to allow the entropy to dominate and for the material to be a solid solution, to be a random solid solution. Most binary mixtures have enthalpies of mixing which are higher than 14. So if you don't, so there's lots of areas where you don't get that entropy dominating, and that's when you get into multi-component phase space with multi-phases. But there is still lots of capability of staying within the 15 range, and so the enthalpies are low, and you then get the random solid solutions. Now let's look at the lattice strain. So in the Cantor alloy, chromium, manganese, iron, cobalt, nickel, these are the Goldschmidt radii. They range from 125 to 128 picometers, and the size difference is therefore about 3 picometers, about 2.5%. Now that's a big lattice strain. It's a very small distance, of course, even compared to the size of an atom, but it's a very big lattice strain. 2% strain in a material produces an enormous amount of strain, energy, and an enormous amount of local stress. That's why if you get much bigger deviations, the enthalpy of mixing becomes bigger and the solution breaks down. If you add aluminium and copper into the Cantor alloy, you can't add it in equal proportions, but you can add about 5% of aluminium and you can add about 10% of copper into the Cantor alloy and still keep a solid solution. And that's because the size difference has got bigger. But remember 3 picometers in the Cantor alloy. Now, is that a reasonable estimate? Well, yes, it is. The synchrotron X-ray diffraction experiments show 4.8 picometers as the actual lattice strain. And a neutron diffraction from the Cantor alloy shows typical lattice strains of 2 picometers. So 3 is not a bad, the Goldschmidt radius is not a bad estimate. It's a very crude estimate, but it's not bad. Well, what's the effect of that? The effect of that is, I'm going to now talk about the effect of that on diffusion and on slip. The first effect on diffusion is that it stops atoms from moving so easily. They can't move through this strained lattice, which has all these local strains. An atom moving, most atoms in FCC move by vacancy diffusion. So you have a vacancy, an atom jumps into a vacancy. But as that happens, as the vacancy moves around, it's moving through very strained lattice. So it's much harder for it to move. And this was first seen by Tsai et al., one of Jingwei Ye's colleagues in Taiwan. But the definitive work was done by Vaidya et al. At IIT Madras, because the earlier diffusion experiments were done by just using diffusion couples, which are very hard to analyze. They're hard to analyze if you remember your undergraduate days. They're quite hard to analyze in binary diffusion couples. although we can do it and we learn how to do it. But once you get to multi-component systems, the de-scrambling the different composition profiles of the different components is very difficult, and you have to make lots of approximations. So the best thing to do is to do tracer diffusion. The first tracer diffusion studies were done by Vaidya et al. And these are the first results, which have been confirmed by a lot more recent results. So initially, Tsai et al. Thought that the diffusion effect, the slowing down of diffusion, they said it was very large. Then some people came along, did experiments and said, well, it's not that large. And finally, Vaidya et al. Sorted it all out by doing tracer diffusion, which is what you need to do to get good diffusion results. So here are the bottom three lines here are Cantor alloys of different compositions. The middle one is the original Cantor alloy, then the others two are different compositions. And the top three lines here are pure nickel, an iron nickel alloy, and an FCC iron nickel and an FCC stainless steel. And we're plotting the diffusion coefficient against the normalized temperature, normalized to the melting point. And you can see that the Cantor alloys are slower by between half an order of magnitude and an order of magnitude than the other FCC materials of similar kind of components, but not multi-component. So there is a slowing down effect. People pointed out that it isn't simply related to the number of components. The more components you have, the more likely it is that diffusion will be difficult, but it depends which the components are. If you have manganese in the material, because of its larger size, and its higher enthalpy of mixing, it slows down the diffusion more than if you have some other elements in there. So that's the diffusion effect. Now that's very important because it means that the materials, the Cantor alloys, are very resistant to degradation in different ways. They're resistant to degradation at high temperature. They because the diffusion is slower. They don't decompose so easily. And lose their structure. They're resistant to degradation by corrosion and oxidation because the atoms can't migrate to the surface so easily. And they're resistant to degradation by radiation. So they're radiation damage resistant because the damage that's caused is fixed in place and doesn't migrate around to create pores, which is the real problem when you get radiation damage. So this is a very important effect, the diffusion effect. Let me go on now to talk a little bit about, when I can get the next slide to come up. There we go, the mechanical properties and the slip behavior. So Otto et al., who are at Oak Ridge, partly at Oak Ridge and partly at the University of Tennessee, did some very beautiful experiments. So they made the Cantor alloy, the 5-component Cantor alloy. They made it and they recrystallized it for different times to get 3 different grain sizes, as you can see here. Equiax grain sizes, very nice, beautiful structures. If you look in the electron microscope, they consist of grains, which are very clean, the occasional annealing twin. And the mechanical properties look like this. So this is the one I've shown you before. Sorry, this one here. Room temperature. It has a room temperature of the Cantor alloy. It depends on its grain size. It's not quite so good at a big grain size. It's better if you have a smaller grain size than 4 microns, if you go to 1 micron. So typically the yield strength is about 400 or 500 megapascals. It's got a ductility of 50 or 60%. If you, depending in detail on the grain size and the temperature, because if you go to lower temperatures, it's got even more ductility and a higher, but it's typically between half a gigapascal and around about half a gigapascal to 2/3 of a gigapascal yield strength, but between 2/3 and 1 gigapascal ultimate tensile strength, and between 50 and 100% ductility. And how does it deform? Well, it deforms by simple dislocation pileup. You get what's called planar slip. These are individual dislocations which slip on a single plane and they pile up, which create barriers, and then that you nucleate a slip on other planes, and so you get these pile-up barriers here, and that's how the deformation takes place. This is exactly the same as you would see in pure copper or pure gold. There is an important difference, which I'll show you in a second. At low temperatures, you get an additional mode of deformation, which is more common than it is in most FCC materials. You get twinning is easier. And that's quite important because it gives extra deformation capability. But the strength is very high for an FCC material. It's not like FCC copper and FCC gold. And the reason is these small local environments being so different. So as here's a dislocation line. Sorry, this black line is the dislocation line. And it has to move as it moves through different local environments. These are not meant to be different atoms. They're really meant to be different local, well, there could be different items or different environments. So the dislocation becomes very organized like this because, and as it moves, it's got to judder forwards to get through the local strains. And that is what dominates the deformation behavior. And that's what makes the Cantor alloy much stronger than a single component FCC material or a simple 2-component solid solution single phase FCC. And overall, the flow stress, that's not French stress, that's flow stress, is given by a sum of 3 components. There is the basic yield strength at large grain size, and that's this component, together with a work hardening component. So as you get the dislocation pileups, the flow strength gets higher, conventional work hardening, and a grain size effect, because if you make the grain small, the dislocations have to move through the grain boundaries. Now these 2 effects are well known, and they're no different between the multi-component alloys and the single component pure materials. This is what's called Taylor hardening. Work hardening is proportional to the dislocations to the square root of dislocation density. This is grain boundary hardening, which is proportional to 1 over the square root of grain size. So we know about these. These are absolutely standard. The special feature is this one. This is the one that's much higher, the basic yield strength. For a while, people thought it was the pile strength that was higher in these multi-component alloys, but it's not the pile strength. It is that difficulty of moving the dislocation through the strained lattice. And this is quite hard to get a theory of, but this is the best theory we have at present. And it depends upon these deltas. These deltas are the sizes of the individual atoms. So you've got each component I has a percentage, an amount of component X, and a distortion D caused by its size, which is different from the other ones. So this is at the heart of what makes that yield, that yield strength. And if we compare that theory to experiment, this is what's shown. This is the Cantor alloy here. This is a modified Cantor alloy with 1 less component without the manganese. People are interested in that because manganese is not the best component to put in materials because it oxidizes a little bit easily. But you can see the black dots are the experiment and the red dots are that theory, the equation I've just shown you. And you can see there's pretty good experimental agreement, and the same over here. And this has now been confirmed in quite a few different materials, much more than this. This is the first work that was done on this by Val Venetal. It's actually Bill Curtin, who is the who's well known, who's at EPFL in Lausanne, is the person who first began to apply this kind of theory to these materials. And if you look at the dislocations, 2 effects I want to show you, looking at the dislocation in more detail. This is the wiggly dislocations that I showed you, caused by the local lattice strains. We can see the deviation of the dislocations caused by the local lattice strains. In fact, if we go to high resolution electron microscope, that's one way of measuring the local lattice strain, because you can actually see the deviation of the lattice of the planes of atoms. But this is but the dislocations are, it's got a low stacking fault energy, which is why the twins form. Again, just the same as copper and gold. So the dislocations separate into partials, and the partial separation varies along its length for just the same reason. The local structure is different here to what it is here. So you get different separations. Same here, you can see. We'll leave that. So what about its uses? So just very quickly, I'm going to mention the uses just for a punchline, because this is what now people are doing. You know, the thousands and thousands of people, there's big multi-million-dollar programs in every country, China certainly, and US certainly, but Germany and France and Australia and plenty of other places, Taiwan, of course. Britain not so much actually, but there it is. Most of the developed countries have very big programs because of the potential for discovering new materials with better properties, and a lot of better properties. So first of all, you've seen that at low temperatures, they already have the Cantor as the best cryogenic properties that have been developed, but they're also being looked at for high temperature strength. And of course, we're using our metallurgical methods to improve them. We're adding components like aluminium, which then produce little nickel aluminide hardening precipitates, or carbon to produce carbides. And we're changing the twinning capabilities, and all sorts of metallurgical tricks which we're familiar with. But we're starting from a much higher, much stronger, and more ductile material with a much better balance of strength and ductility. So people are very interested in cryogenic and high temperature strength. I've already said that the corrosion resistance and the radiation damage resistance is high because of the basic diffusion resistance. Some of the other materials, not the Cantor alloys, are being looked at for functional materials, for solar energy conversion, high temperature superconductors. We're finding new ceramics, and we're finding lots and lots of new materials with new potential applications. I'm currently working on the recycling and reuse. I mentioned that at the beginning. The problem we've got with recycling, and we recycle 95% of our metal usage is aluminium and steel, and 50% of it is recycled. But you know, we recycle it back to the smelter. What we need to be able to do is not resmelt it. That's treating the recycled material as if it was ore, but it's much already been gone through lots of processes. So what, you know, and if we put it back into the smelter, it's still going to have to be smelted and then remelted and then forged and then shaped and all the rest of it. And that's where most of the energy use and most of the carbon emission comes from. So we've got to start to use more generic alloys, which we can just remelt and reuse, or even better still, just reshape and reuse. And to have generic alloys, we need to be able to contain all the impurities which are in the existing alloys when we remelt them. So that they're really multi-component systems. So that's another important potential use of these materials. Now I'm going to finish, if I can go on to finally onto the last little group of slides, by showing you 3 or 4 slides which I came across when I was Vice Chancellor, Vice Chancellor is the same as President of the University of York. And I was from about 2002 to 2013. And the head of the chemistry department was a man called Paul Walton, who specialized in looking at the effect of different elements on the body. And he used to give the chemistry of it. He was a chemist. But he used to give a wonderful lecture to school children, and he used to show these slides. And I thought it was a wonderful explanation of the importance of multi-component materials. So he would show school children this slide, and he would say to the school children, do you know what this material is? It's a well-known material, and a lot of these would be school children, maybe aged 10, 11, 12, or 13, and they'll have come across carbon probably, some of them. They'll have heard of carbon. And so some of them put their hands up, maybe all of them, and they say, yes, sir, we know what it is, it's carbon. And he'd say, yes, very good, well done. Then he'd say, well, here's a harder one. This is another material. It's a bit more complicated, isn't it? Do you know what this is? And of course, some of them would have come across water, and it has the formula H2O, and a lot of them would still put their hands up and say, yes, we know, please, sir, we know what that is. It's water. It's H2O is water. And he'd say, yes, well done. And then he'd say, and here's a harder one again. What's this material? Well, I'll let you think about that, but I've already given you the game away. The school children wouldn't know, of course, but I've given the game away up at the top here. It's the secret of life. This is the chemical composition of your body. It's the chemical composition of my body. It's the chemical composition of everybody's body. It's actually the chemical composition of dogs and cats and horses. We all have the same, in chemical terms, we're the same. Living things, living mammals have pretty much the same chemical composition, and it's this. Now, these are not percent, the 650,000 carbon atoms, over 4 million hydrogen atoms and so on. It's very precise. There's one atom in a trillion, in more than a trillion. something like one atom in a trillion is selenium. Something like 10 atoms in a trillion is cobalt. If you have, instead of 1 atom in a trillion selenium, if you instead of having 1, you have 2, you can't survive. You have to, it's very precise. If you have none, you can't survive. So humans need that 1 atom in a trillion of selenium. We don't fully understand quite why. We need those 10 atoms of cobalt. We need those 100 or so, or 200 atoms in a trillion of silicon. This composition is very precise. If you get any of these slightly deviate and slightly change, I'm afraid human life is not possible and you die. So selenium poisoning is actually quite an issue at the moment, because the way the world's agriculture is going, selenium is being removed from a lot of our crops. So people take selenium supplements, which doesn't work because they don't dissolve in the body anyway. So it's a bit more complicated than that. Actually, it's quite easy. You eat Brazil nuts because Brazil nuts have selenium in a form which will allow you to absorb it. But the point I'm making here is, somewhere in the middle, that multi-component phase space, that 60 or 80 or 120 component, whichever way you want to think about it, there's a polyhedron, the equivalent of the triangle or the tetrahedron. There's a polyhedron with 60 or 80 or 90 or 120, if you want to include everything, corners. There's a polyhedron which represents multi-component phase space with all possibilities. And there's a point in the middle of that, which is human life. And there are lots of other points which are very special, which we haven't yet found. And there are lots of other wonderful new materials to find. So my closing statements are that 3 of them are the same as I started with one new additional one. Human history is the history of new materials. All materials are alloys. I hope I've persuaded you of that. I hope I've persuaded you of this. There are gazillions of materials. I hope I've persuaded you of that. And there are literally wonderful new materials to be found. The thing that has restricted us is our ambition and our what, I don't know what you call it, but our desire to go and discover new worlds. You know, the Industrial Revolution grew out of the scientific revolution, you know, Galileo and Newton and all those wonderful developments. And that, it's been argued very forcefully recently, grew out of the age of discovery, when people began to sail the seas and began to find things. It's all about looking for new things. In classical times, in traditional times, people didn't look to find. So science is as much about discovery, about exploration, as it is about theory and an experiment. So that's very important. And I've discovered this in my lifetime, because I did lots and lots of different things. And the most successful thing I've done, it turns out, was the most crazy one that people said, that's crazy. Why would you do that? Why go there? And the answer is, sometimes you find exciting things when you go to different places. And there are lots and lots, we now know, of new materials to be found. And I say to all of the students in this audience, you have the best, you're in the best subject that there is. You know, it's a bigger subject than astronomy. There are more more materials in the world to be found than there are atoms in the universe. So we've got more interesting things to discover than the astronomers, even though the astronomers make more noise than us. And that means there are literally wonderful, so you're in a great field where there's lots of things to be found, and there are some fabulous new materials to be found which have great properties. So if I can get onto my final slide, thank you. Thank you very much.
Yeah, thank you, Brian. Thank you. The audience here give you a close, and you couldn't see them, the camera. Now is the discussion on the content of Brian's lecture. If anyone, firstly, the audience in the lecture room, in the meeting room, conference room. If anyone have a question, I would like to invite you to come forward in front of camera, to stand in front of camera, because we do not have a bigger camera to see you there. Thank you very much, Brian, for a very interesting lecture, and also the update on the science and potential applications of high entropy alloys and the Cantor alloys, and also you talk about the energy, whether it's the energy conversion materials and also the high temperature superconductor. Presumably they are the ceramic based, oxide based, not alloy, because is that right?
They're alloys, they're oxide alloys.
Yeah, the oxide alloys. Okay, yeah. But that makes me think, how about if we oxidize the Cantor alloy to produce the ceramics from it? You know, could we get something? Yeah,
I haven't tried it.
Something.
But what people have discovered is if you take the spinel structure, you see what happens in multi-component phase space is this is a tricky point which I didn't mention. Why is it that there's a great big region of face-centered cubic material? And now one level of explanation says, well, you've got, and I've already given you this explanation. It's the explanation that Jinwei Ye gave, who's the co-founder of this field with me, the Taiwanese man. And he said it's high entropy, and that's why he gave these alloys the name high entropy alloys and high entropy materials. He said it's because of the entropy, and in one sense that's true. But then the more interesting thing is, why is it that when you go into into multi-component phase space, that the structure of the space is different to binary and ternary and ternary, because you get entropy effects in binary and ternaries, and the answer is really a bit more complicated. So what actually happens is this: if you're in binary and ternary systems, when you add components to other components, they form compounds, don't they? And then they form more complicated compounds. So if you look at the binary systems, you know, the one component systems, there's a certain number of crystal structures. If you add two components, you can have more complicated crystal structures with two sublattices. So, you know, nickel aluminide, Ni3Al, is like an FCC structure, but you know, but the face centers are one component, and the corners are a different component. You've got two sublattices. The same is true of any oxide. An oxide structure is a structure where there's different sublattices for the oxide, for the oxygens, and for the metal. So if you take, and the same is true for rock salt, sodium chloride. You've got a cubic structure with sodium and chlorine as different sublattices. If you go to a ternary system, same thing happens. You start to find some more ternary compounds, but you don't get so many more. And the reason is, it's hard to have too many sublattices. If you then go to multi-component, you don't get any more compounds. Why don't you get any more compounds? Because you can't have any more sublattices. It's something to do with the fact we live in three-dimensional space. So, you know, having 10 components, you can't find structures with 10 different sublattices. It's too, you know, you can't pack them in three-dimensional space. So because you don't make different compounds, it means that there aren't competing new compounds to compete with the solid solutions of the existing compounds. What happens is, things that are line compounds or very restricted solid solution compounds in a binary system, because there's no competition from ternary or quaternary compounds, they start to expand out and become much bigger in composition. So as well as having FC, to FCC, pure nickel, pure copper, pure gold, but you get into multi-component space, and suddenly they're all mixing in a great big patch. Same thing happens with the borides. So if you take titanium nitride, it's got a rock salt structure, I think. And the same is true of vanadium nitride, and the same is true of hafnium nitride. If you mix them, they form a solid. No, they've got a very fixed composition. You can't change the nitrogen titanium composition very much in titanium nitride, but you can mix it with vanadium nitride and hafnium nitride, and you get what I call a multi-component compound. So it's another solid solution. You get titanium, vanadium, hafnium with brackets around it, N, and you can also replace the N with some carbon. So you can have a carbonitride or a carboboro-nitride. And you find that you've got a multi-component material in multi-component phase space, and there's a big patch of this with a big range of composition now, varying the metal, keeping the fixed metal to boron, to metal to non-metal ratio the same, to keep the rock salt structure with the two sublattices, but with a big solid solution on the metal sublattice and a big solid solution, multi-component solution on the metal sublattice and a multi-component solid solution on the non-metal sublattice. The same thing happens with spinels. When you take spinels and go to phase space, you can mix. We already know that you get a range of compositions of spinels in ordinary, even in ternary systems. But when you get into multi-component phase space, there's an enormous region of spinel structure, all one solid solution region. The same thing happens with the Lavis phase, which is again, there's some room for composition variation in binary system in Lavis phases, but you go into multi-component phase space and suddenly they expand into great big sacks of literally hundreds and millions of compositions. So within those structures, it's possible to look and try and find energy conversion materials, superconductors, and so on. And people are doing that now.
We got a written question here in Chinese. I say actually I agree. Actually, the cost of high entropy alloys as well is really high because you have this contain a high percentage of the expensive elements like cobalt. So how do you think the future applications of such alloys? The potential. Would you want to comment on that?
Well, it all depends.
Yeah. Anyway,
cost is very important. Cost is very important for our immediate application. Of course, it is. But when nickel superalloys were first invented, they were extremely expensive, and people weren't sure we could use them because they were so expensive. If we need them, we'll use them. At the moment we've developed these wonderful materials to create lithium batteries. Without that, we couldn't have it. Most countries are now aiming to have electric cars by the end of the next two or three decades. We can only do that because we developed improved battery materials. Battery materials depend upon very expensive components. Lithium, samarium, and cobalt actually are important in those, and cobalt's very important in transformers. So in high, in low loss transformers. So and hard magnets. So I don't think, of course, in the first applications, people must look for that. They must look to get rid of the high cost as far as possible. And people are looking for that. Of course, they're looking to try and find those properties. But if you take iron, nickel, manganese, they're not nickel's fairly expensive, not as expensive as cobalt. But if you take iron, chromium, nickel, manganese, and you can add aluminium, there's plenty of low cost metals that can be added, and people need to look for it. I think the answer is look into it.
Yeah. Okay. Here we got another question from YYL. Anyway, you might want to tell your name and organization so that Professor Cantor will know. This another question. The FCC high entropy alloys always possess. You can see this. You can always possess good work hardening ability. We know. While for the BCC high entropy alloys, the working hardening ability are very generally poor. So, what is the possible reason? Brian, you want to comment on that?
Yeah, well, it's the same as in pure materials. The in pure components, the work hardening of BCC is less good than FCC. But the basic reason is exactly the same. You don't have enough slip systems. You have fewer slip systems in BCC than in FCC because in FCC they're sliding on different planes. They're on
so that's supposed to
instead of 110 planes.
The interactions
That's the basic reason, but the details are very complex, and people are looking into it. By the way, work hardening isn't the most important thing because the BCC Cantor alloys have got fantastically high yield strengths. We already have now BCC. I call them Senkov alloys because Oleg Senkov was the first person to make up. I won't remember exactly which components it was: vanadium, tungsten, titanium, niobium, and molybdenum, I think. Anyway, but some of those early transition metals with a BCC solid solution. But I can't give you, I don't know, I'm not as familiar with the BCC alloys, but people have made BCC high entropy alloys with yield strengths of 2.5 gigapascals and still a few percent of ductility, maybe 5% ductility. So I think it's a little bit like the FCC ones. People are still trying to improve the strength, and they're trying to improve the strength by traditional metallurgical methods. By for the FCC materials, they still want to make them stronger, and they're trying to do things like make them have small precipitation hardening, make them control the strain hardening through work hardening, the traditional things that we do, but use transformation hardening by allowing them to transform. So there's classic hardening methods being used for FCC materials, and there's quite a bit of work being done on that now. The BCC materials, a lot less of work has been done, but people are there trying to improve the ductility. But they start with a fantastically great strength. There's plenty of room to back off a little bit on that and improve the ductility. So I think there's some great combinations of materials are being developed as we talk, because there's so much work going on.
Okay. Yeah, thanks. The next question is, I would like to ask it's M. He asked, I would like to ask the influence of short-range order structure on dislocation slip mode. High entropy alloys. Whether it promotes plane slip or wavy slip.
It's a good question. Well, I didn't talk much about short-range order, but of course, the Cantor alloy itself. So let me just deal with the Cantor alloy itself, which has got 20% of chromium, manganese, iron, cobalt, and nickel. Now it's very near to being regular. It's very near to being a regular solution. In fact, it's very near to being an ideal solution. There's been quite a lot of study now which shows that it's got very little short-range order in it. There might be a little bit of short-range order. There's a little bit of a tendency of manganese and nickel to congregate together rather than iron and cobalt, and so there is a very slight degree of short-range ordering, but it's very, very slight. It's almost undetectable. So the Cantor alloy itself is, I think we can say to the best we can measure, is ideal. So in that material, there is no short-range order, but of course the dislocation slip is still shows all these characteristics. That the dislocation slip is not easy, and you have this because of the local lattice, local structures, the local atomic structures, and the different, and the local lattice strain. So it's not enough lattice strain to change the short-range order, but it is enough lattice strain to restrict the dislocation slip and give you pretty high, not super high, but pretty high basic yield strength. And then, as you rightly say, work hardening. Now, if you go to non-equiatomic compositions, or if you change and add in some other components and have different basic components, even equiatomic, if you say add copper and take something out, so you get an equiatomic, or take out the chromium or so on. If you change the composition, go to different places within the FCC region, within the Cantor alloy region, you begin to see more short-range order, and people have measured the short-range order. Obviously, if you go far enough, that short-range order begins to manifest itself by interactions between the atoms, which lead to compound formation, and you move outside the single-phase region. And that's an important region too, because then you're starting to get the precipitation hardening. Now, the question is, what happens to so you start to see you can start to see short-range order. And does it promote the planar slip or the wavy slip? I don't know that much detailed work has been done on it, but I think we would expect that with the short-range order, it would promote more wavy slip. And it would depend a little bit, though, on the stacking fault energy, because obviously it depends whether, if you've got separated partials, if the stacking fault energy stays reasonable, then it's harder to have wavy slip, because the partials are more, once you have partials, they're more fixed in the same plane, and that's what creates planar slip. So it depends. I think, you know, I don't think we know is the answer. There's a lot to be studied. We've only in the last couple of years really understood the Cantor alloy itself, and that's the one alloy that's been studied really a lot. And people are beginning now to study these in more detail, these other compositions. But I think we can expect that, you know, depending which composition you change and depending which kind of short range order you get, you will in some cases move to more wavy slip. It'll be those cases where the stacking fault energy becomes higher, so that you prevent the partial separations, and there'll be those cases where the short range order becomes more effective too. So I think we know what's likely to happen, but I think we need to do the studies because it won't be exactly the same as we expect. One of the interesting things about these materials is they have the basic behavior that we're familiar with. They look a lot like ordinary FCC materials. And by the way, the spinels look a lot like ordinary simple 3-component spinels, but they have special differences. So we find they're a bit like, and we've got good theories for them, but we have to modify them. So the answer there is, you know, it's worth looking at, but we don't really know in detail yet. Titanium, someone's asked. Can titanium become one of the important components? Yes, is the answer. Titanium dissolves a little bit into the Cantor alloy, and it's one of the big components of the body-centered cubic Senkoff alloys, which are being looked at particularly for aerospace applications. So I think the answer is yes. Who's the administrator? Is that you? What's the difference between short-range order and clusters or clusters? Well, it depends on your terminology. A short-range order is the same thing as clusters, to be perfectly honest. It depends when you want to call a cluster a precipitate or not, and that's, I think, that's like beauty. It's in the eye of the beholder. You know, you need a definition as to when you want to say a new phase has formed. When it's normally, when it's only at the first near neighbor or second near neighbor level, it's normally called short range order. And when it gets a bit beyond that, it's called a cluster. But you know, of course, classically clusters are not spherical anyway. They tend to be platelets or rods or something. So that's when the short range ordering becomes, you know, more extensive in one dimension or maybe 2 dimensions.
This question about the opinion about the most fundamental difference between high-entropy alloys and conventional alloys, since in many cases the mechanical performance of FCC and alloy is comparable.
No, I don't agree with that. I think it's comparable or better. You're misunderstanding. You know, what we have to do is the Cantor alloy itself, the single phase, what most of the work's been done is single phase FCC. You have to compare that to pure copper, or if you like, pure iron, or you know, or pure nickel. And the answer is it's got much better properties than a pure FCC single component material. Then we can modify its properties by adding other components to produce precipitates. And so if you add, I mean, in my review, which is published in Progress in Material Science, it's not actually been fully published. It's in press and it's up on the website. So that's just coming out. And when I looked it up, we have now found by about 3 or 4 different methods, we've been able to get up to between 1 and 1.3 gigapascal yield strengths with still at least 10, maybe even 30 or 40% ductility. That's better than any possible current material, metal material. Yeah. So I don't agree with you. The best are better, in both fracture toughness and in strength. You know, it's just clear. It was clear on my Ashby graph. So I'm sorry, I don't agree with you.
That's okay. That's good.
Of course, there's lots that are very soft, just like pure copper is very soft, and there's lots that are very brittle. If you put enough things in, it'll become multi-phase and it becomes brittle. So we're still exploring all that, but we've got some we've only begun to try and explore it to try and make it good. It took us a long time to develop the good quality high strength steels and nickel superalloys and so on. Give us a chance to get the really, but the base starting material is much better than the base starting material of pure copper or pure nickel or pure iron.
Okay, here we have two questions asked in Chinese. So let me ask. Paul asked, some scholars think that high entropy alloy, multiple component high entropy alloys, like alloys, the design of them make some elements not easily recyclable, and also cause the waste of resources. I suppose thinking about the use of the expensive elements. So how do you think?
Some will, some won't. Look, there are millions of alloys. Some are good, a bit like the last question. Some have got good mechanical properties, some have got bad mechanical properties. The point is there's literally millions to go and explore and try and find the good ones and find the best ones and make them better. And the same is true here. Of course, some of the components, if we start using them, might create problems. But just think about it this way: we're using lots of different materials, what we've got to do is we've spent, the way I think about recycling and use of resources is this: we have spent about 150 to 200 years. We've spent actually longer, but if we think since the Industrial Revolution, since we've had serious alloy, metallurgical alloy development, scientifically, we spent all that time making ever more refined components using ever more refined alloys. I don't know if the people in the audience know, there are about 10,000 different steel grades. Might be 20,000. I don't think we need 20,000 steel grades. Why do we need so many? You know, and that causes problems. And the reason we got so many is because every specialized component has had a specialized alloy developed for it. So we've designed components and alloys together. I mean, we've done a fantastic job. That's been our technological development has been based on that. It's been based on getting ever cleverer and more effective components based on ever more clever and effective materials. By the way, the material scientists have never failed to deliver. When people say we want X, give us enough time and enough money and we will deliver X. You know, we deliver improved high temperature performance. We've got the improved high temperature materials. If we work harder, we pushed up solar energy conversion. You know, if we keep working at it, we find that's because there's all these new materials to find. So if we keep looking, we will find it. But we've done it on an ever more precise thing. The problem of resource usage is we've got to get more generic. We need to have only, you know, we're never going to use a mild steel type composition for a stainless steel. So we're going to need some stainless steels, we're going to need some tool steels. We're going to need more than one composition of steel, but we don't need 20,000. What we need is maybe 50. And then we can convert. Now, in order to have those, we probably will have more alloy components in all of them, so that we can recycle them easily. Because when you recycle them, you pick up impurities. So we're going to have alloys which are more resilient to having impurities in them, and therefore are more multi-component and are more generic. So that's I think where we've got to go as far as resource usage is concerned. And of course there'll be some very resource in, you know, but you know, which we want to conserve, and we have to be very careful not to use them.
That's good. Yes, I agree with you actually. I suppose I mean, it's all because of the history of the steel development. There's, you know, I don't think thousands, but hundreds of compositions with minor composition differences. If we want the whole world to need only like, virtually I agree. I think in terms of the properties, probably need only like 50 grades of steel.
Yeah, maybe
and
100.
that will make the recycling much easier.
Yeah, maybe 200.
Yeah,
you know,
200, because then, you know.
I think 50, but maybe I'm wrong. Maybe we need 200, but we don't need thousands. We've got.
Sure.
By the way, aluminium alloys is the same issue.
Yeah. Here we have another question asked in Chinese. Because of the lattice strain or lattice distortion, lattice string effect, why we have to select elements with smaller differences of atomic radii in design of alloys. You understand the question? Yeah.
No, say it again. Say it again. Because
see, I suppose the meaning of the question is because the lattice string will strengthen the alloy, make the alloy stronger of the hydrogen alloy.
Yeah.
So why, when we design the hydrogen alloys, we still need to select? He did not say proportion for any alloys. Why we want to still select the elements with the smaller differences between the radius?
Okay.
Atoms. Yeah.
Okay. Look, it's a balance. It's a balance. If the special properties of the solid solution, FCC alloys, the Cantor alloys, are caused by the local lattice strains. That's what makes the diffusion slower. It's what makes the dislocation slip more difficult, which makes the starting yield strength higher, even though it's face-centered cubic and has got tremendous ductility. So just to repeat, because some people think that it's got bad properties, compared to copper, you've got the same enormous ductility, but you've got a much higher yield strength in the Cantor alloy. And that's all because of these local lattice strains. So you've got local lattice strains, which give the resistance to diffusion and the resistance to dislocation slip, and some other properties of that sort. By the way, there's some interesting electrical and magnetic properties caused by those local variations as well. But the question is, so if you don't have any of that, if all the atoms are the same, we know if you've then got pure copper and you don't get those effects. So you want those effects. On the other hand, if you put in atoms with bigger differences in size, then those differences in size lead to other things. They lead to the breakdown of the face-centered cubic crystal structure, and you start to have other phases, and the material begins to be multi-phased. Now, initially, you can use that to give precipitation hardening, but only very sensitively. If you do it too much, you start to have, like we know in binary alloys, you start to have a brittle lot of intermetallics, and material becomes brittle and unusable, or you lose the properties. So it's a subtle thing. We want to have those lattice strains, and we want to have some difference in the size of the atoms, and we want to have some enthalpy of mixing, but we want to have it small enough. We want to have it to create some of the special properties, but we want to have it small enough that it doesn't break the single phase structure, because then we get into other problems.
This question from Carl 3 asks, thanks, Brian. This is fantastic lecture. In your opinion, what are the general criteria to choose the elements from the periodic table to make good high energy values?
Well, that's a good question. So very early on, I'm currently writing a book on multi-component materials, and I'm currently writing the first chapter is the history of alloys, the thing I talked about at the beginning, just to set the context. I've written that. The second chapter is about the discovery of multi-component alloys, and I told you some of that in the second bit of my talk. But I didn't mention one aspect, which is this. We began just by trial and error. We just made up some materials and saw what we got, and we found things. Now, there's a lot of work as I began to think, how can we do better? How can we have a better, we can't go by trial and error all the time. We will have to use trial and error. Experimental trial and error in the end is absolutely crucial in this area. But surely there must be ways of looking which can be more structured, let's say. So the structured way that I began to think was, why don't we take materials where we know there's good materials, but then make one of the components multi-component. So that's how we make some of these compounds. So that's effectively what we're doing when we make the sort of multi-metallic boride, or the multi-metallic nitride, or the multi-metallic spinel structure. We're really taking a material which has got two components, and we're now multi-componenting just one of the components with some similar components. So that's one way of thinking, and people are doing that. So they're taking materials of interest. The first work we did was on an amorphous alloy. We took an amorphous alloy composition, which was a mixture of 60% late transition metal and 40% early transition metal, and we varied we changed this. We stayed with 60-40, but we changed the number of early transition metals and the number of late transition metals. And people have done that a little bit, but not very much. And we found what's more amorphous materials. You can do the same thing, starting with, and people are doing this with, let's say, ceramic oxides or ceramic nitrides for strength, high strength ceramics, or you can do it for functional materials as well. Because I see Gang Shah, another question is, can we use functional materials? Yes, and that's the approach that's being taken. So there's a lot of work going on at the moment on nitrides, borides, carbides, oxides, to try and find new functional materials, but using the multi-component approach. So that can be done. But let me go back to the basic idea. So that was my idea for how we might use a more structured method. It's still a bit of trial and error. Now, there are other methods, and people are using them. People say to me, why don't we just use thermodynamic simulation? You know, we've got all these wonderful things like thermocalc, tell us what will happen. And the answer is, it helps, but it doesn't help very much. You go and try and look up on thermocalc, or do a thermodynamic calculation on a thermodynamic database for a 7-component or 8-component system, and you'll find that a lot of the data is missing. Of course it's missing. We've never made those alloys up before. So we don't, thermodynamic calculations only work when you're within the range that you've already got some data, and they've already got quite a lot of data to be successful, to be honest. So the problem is that our thermodynamic understanding is all based on existing materials. The data is based on materials, the experimental data that we use, and the theories are based usually on dilute solution approximations. So our thermodynamic calculations help us, but they don't help us to extrapolate into the middle of multi-component phase space very much. They're an aid, and it's helpful to use them. The next thing that people say to me is, well, why don't we use density functional theory? We've got really good at predicting materials from fundamentals, from first principles. Great idea. But the same issue applies to thermodynamics. That's just a more detailed version of thermodynamics. Thermodynamics is a sort of high-level, black box way of talking about the properties of materials and stuff. Density functional theory is a much more detailed way of talking about the same thing. But the same issue applies. Our theories and our data, density functional theory relies upon lots of parameters and data which we have to plug in. And we need to know those. And if we don't have them, and we don't have them for multi-component systems, we can't then do the calculations. And we also, the approximations are made depend upon the dilute solution. So it's the same kind of problem. The last thing that's mentioned is the use of...
杜金涛，你别共享屏幕，我们看不到那个谁。
应该。
你把那个共享屏幕关了，那个谁。
他也没共享什么东西，好像是。那个 I can't help but chip in and ask Brian a question.
Yeah.
Brian, can you hear me? Right. Okay. First of all, really, congratulations on such a great lecture. I think you surely are well positioned to give us such an account on this history of materials, given your experiences. So I hope that's a compliment. Okay. Now, now, of course, I'm not working in these high entropy alloys, but I do have colleagues. They did some excellent work with a paper in Nature or Science, recently. I did have one question. When you have, say, 5 components or elements, if you assume you try to make this alloy by adding one after another, will the sequence of adding these elements will affect the final product?
In general terms, no, because most of the materials are made by most of these multi-component alloys are made by melting. and if you melt them, then it doesn't really, it might matter a little bit if there's issues around oxidation or vaporization. So you want to add those things that will oxidize or vaporize more easily towards the end. But in general, melting practice knows how to handle those things. So the truth is, if you're making them that way, then the answer is no. But there are other methods of making multi-component systems where it may matter, because you're sort of adding, you know, I hear the line of thinking, because you've already got a certain material, and so it's harder to get the extra elements to be added. So I think it can depend. If you're doing it like, say, additive manufacturing, but people are making multi-component systems by kind of controlled deposition of different elements, which then diffuse together, and it may well then matter which order you do it.
Right. Okay. Thank you, Brian.
No problem. Delane, can I answer this question here from Wen?
Yeah.
It's a good one. Who's asked, it appears new results developed from ideas transferred from traditional low entropy alloys like precipitation strengthening, nanoprecipitates, improving ductility by TRIP and TWIP, dual phase structures, eutectic entropy alloys. Absolutely. This is what's happening now. This is what I said before. The Cantor alloy is just a starting point. Now we do our metallurgical magic. We do our metallurgical, what you call low entropy understanding. We do precipitation strengthening, we do nano precipitation, we do grain boundary hardening, we do, you know, we control the grain boundary sliding. If we want to have ductility, at higher temperatures, we can have two-phase structures, we can have precipitates, we can have composite-like structures, we can have transformational plasticity, TWIP, TRIP. We can use, we can control the stacking fault energy to change the twinning possibility. All those things we can now, all those metallurgical manipulations of material, the engineering of the structure of the material to try and control and improve the properties and get the balance that we want. We now apply that, but as I said before, we're starting from a base which is different. So instead of, and we're starting from many bases. So the Cantor alloy, the chromium, manganese, iron, cobalt, nickel, is just one FCC base, which we can do all that to. We can add it, and we've got some wonderful results already. But we can start with other FCC materials. We can start with the BCC materials. That's been done a bit. We can start with these other ones. The potential is enormous, and we're very good at controlling this. Metallurgists have learned very cleverly to make wonderful modified properties by controlling microstructure. We all learn that as material scientists. It's all about controlling microstructure. For a given material, we can get loads of different properties by changing the microstructure. But we've actually got many more materials to work with, so we can start and we can do all that. It's a great question. That's what people are doing now.
Brian, this is related to this question. I'm just thinking, if by any time, within our lifetime, somebody can develop a single phase alloy with a yield strength of, say, 2000 megapascal, and still ductility of, say, 20% or 30%, without using all other, like precipitation hardening, other this two-phase effect.
Oh, we're not far. Yeah, we're not far away. The BCC,
that would be great, isn't it?
The BCC Senkoff alloy, based on the early transition metals, is not far from that. They've gone up to 2 gigapascals with, I can't remember, 10% ductility.
Yeah, okay, that's
maybe more like 5% ductility, or 1.5 gigapascals with 10%. So we're not as high as you said, but we got pretty high. And by the way, I believe it's all out there. Listen, there's a famous metallurgist. I don't know if everybody in the audience has heard of. I'm not sure. I give this lecture to people who are not always material scientists, so I've assumed more knowledge amongst the audience this time, because I think mostly material scientists. But there's a man called Alan Cottrell. Most metallurgists,
of course,
material scientists will have heard of Cottrell. So Cottrell is very famous. In Britain, he was called the father of metallurgy, because after the war, he was the first one that began to use proper physical theory to explain metallurgical behavior. I was just going to say, and I recently was looking at it. Robert Mayle, another famous American metallurgist, thought that was a really bad idea, but in fact it was a good idea because it allowed us to understand metals better. But anyway, Cottrell, he died when he was about 90 or 90 in his 90s. But even in his 80s, he would give lectures, and he gave a lecture which I like to tell people about, called, and I invited him to Oxford in the late 1990s, and he gave this lecture, and he died in the 2000s sometime, called Shocks in Material Science. And he said it's a remarkable thing that you get great shocks of discovering new things in materials science. And he mentioned, you know, we had a shock that we discovered the ductile brittle transition. It's the first thing he worked on. And he said, you know, that because it was, you know, important just after the war when he was, you know, very influential. He said, and then we discovered amorphous alloys. Then we discovered superplasticity, superplastic metals. Then we discovered superconductivity. Then we discovered quasicrystal. We keep having, he said, shocks, and he talked about some of these shocks, as he called them. Now, I thought at the moment, well, you know, that's amazing, isn't it? Why do we keep getting these shocks? And he didn't know the answer. He said, we don't know why, but we keep having these wonderful new discoveries. Well, I now know why. I know why. We've got this amazing array of materials, and people weren't exploring it before. They would only find these things by accident. Occasionally, people would get into a different composition region in multi-component phase space, you know, perhaps by accident. You know, they say that the nickel aluminides were found by accident. The aluminium got into the nickel by mistake, just like penicillin was discovered by accident. So, you know, we would occasionally find it. And, you know, in the high temperature superconductors were also discovered to a certain extent by accident. They weren't looking for high temperature superconductivity. They were looking at some interesting new oxide structures. So we were finding new materials almost by accident, and not really by realizing what a massive continent, what a massive galaxy of materials there is out there. So now we're trying to explore it a bit more rigorously, a bit like we do with outer space. You know, we're sending rockets into multi-component phase space to try and find things, you know, because we might land nearby something interesting. So that's how I think about it now. So that's why, sorry, to finish that, so that's why I say, you give me, yeah, you look for that. I want to tell every student, go and look and you'll find.
Okay, I ask correct and comment. Yeah, for the actual time or report, I gonna ask, could Brian ask comment on where could be the future of hydrogen alloys? Could hydrogen alloys be a functional material for future?
Yes, I've already answered that one. I've already answered that one. Yes, people are looking at that. Yeah. I'm sure they can. Everything's possible. Everything's possible. Listen, Dirac. You know, I was once asked. When I was vice chancellor at York, I think the local paper did an interview with me, and they asked me a lot of silly questions. And one of them was, "What's the thing you most regret in your life?" And I thought about it, and I said, a scientific thing. And I said, I was at Cambridge at the same time as Paul Dirac, the famous physicist, and I never went to one of his lectures. And Dirac was at Cambridge at the same time as me, like Cottrell, but they were famous people then. I was just a student. But Dirac once said, and because Dirac's famous for discovering and predicting the positron, the positive version of the electron. But he had a principle. He said, if it's feasible, it exists. And that's been used quite a bit in fundamental physics. And Dirac came up with that idea. I think that's true in materials. If a material like the human body can exist, there must be some other amazing things. So if you can find a high temperature superconductor, like the ones we've already found, there are some other high temperature superconductors, superconducting materials with even better properties. It's a question of going and looking and finding. If you want to find a 2 gigapascal, 20% ductility material, it's there. You just got to find it. There's a big haystack, but there's a big haystack to look for the needle. You're muted. You're muted, Deling.
Yeah.
You're muted. You're muted.
Yeah. Right. Yeah. Here this question. Thanks, Professor Cantor, for the great lecture. There has been research showing the importance of short range order, but short range order is confined in very small area, small site, not strong enough to influence dislocation slates, which is active in much larger field. Could you give some comments on it?
Yeah, good question. And it seems like it might not have an effect, but the answer is it does have an effect, because dislocation has to slip all along its length. It's no good if it just slips one little bit of it, because then that bit gets then pulled back by the rest not moving. So the truth is that the local regions affect the dislocation all the way along differently. So, you know, it's one of these things where local things can sometimes have a very big effect.
Yeah. Deng Shan asked, many thanks for the great lecture. A follow-up question. Currently, the most successfully developed single-phase iron is the Cantor alloy and its derivative. In other words, the design here cannot be explored extensively like old alloy design wisdom. Is there any solution to tackle with this situation? I agree. They still have not expanded to very widely.
Well, the answer is people are developing those design ideas. So some people are using what I would call heuristic design. That's using sort of rules of thumb, a bit like, say, the Hume-Rothery rules to design the alloys, and there's some quite sophisticated ways of doing that. Sort of structured guesswork, really, but it's you can do a lot of structure in that, and that's being done. But also people are using fundamental, I already mentioned it, thermodynamic and density functional theory to help guide design. And other people, and I was going on to mention it before, are using intelligent design, let's say, techniques, you know, those sort of systems of looking for patterns in data in order to help design. So yes, and that is a very active area. Because multi-component phase space is so large, people are trying to develop all these design methods to try and help, and they will help, but they won't solve the problem. So they will help, they'll contribute. We'll still have to keep doing experiments. So there's lots to find out, Some people say to me, you know, oh, we can do it all with density functional theory, but we can't. We can do it all with artificial intelligence, we can't. We can do it all with thermodynamics, we can't. You know, I love thermodynamics, I love density functional theory, I love artificial intelligence and its systems, but really we've got, you know, the world is a complicated place. It's so complicated that without the human spirit being having, you know, a spirit of discovery and exploration to find things, we can't move. That's absolutely critical, and all these other things are just tools to help us a little bit along the way.
Yeah, thanks, Brian. The time getting late. One of the colleagues in the audience want to ask, would you like to comment? Would you please comment on the corrosion resistance of hydrogen alloys, like Cantor alloys? Which of course would be very interesting. Yeah.
Okay. Well, I said I'm writing my book, and I haven't got to the corrosion resistance bit, so I haven't studied it. It's one of those areas I don't know as well as some others, like the radiation resistance. I've read a little bit about it. So, but basically, but they have found quite good corrosion resistance. Again, in some alloys, you know, people make the mistake of thinking all high entropy alloys are this or that, and you know, people, it's a bit like Professor Ye said a lot early on. He said that there's resistance to diffusion. Then some other people said, well, I found a multi-component alloy which doesn't have resistance to diffusion. Well, of course, there's millions of alloys. You can find anything you want, good or bad. But they found some which are very corrosion resistant, and the Cantor alloy itself is corrosion resistant. And the basic reason is this, that when the corrosion is taking place on the surface, you've got to have migration within the body of the material. You've got to have diffusion between the bulk of the material and the surface for the corrosion to continue. Otherwise, the corrosion stops taking place. You know, So by, or at least it slows it down. So because the diffusion is slower, so the initial corrosion may be the same, but you know, you build up a composition profile below the surface, and it slows down because the atoms have to migrate to the surface or away from the surface. How are we doing, Delang? Are we finished?
Okay, Ron, here is a message. Say congratulations, Professor Brian Cantor, for your curiosity on Cantor alloy. What a beautiful idea, and what beautiful mind. Anyway, I think.
Let me say before, don't go on, because I like that comment. I'm thank you very much. I'm very grateful for a very nice comment.
Yeah, that's right. It's sort of like a open a new thinking of the whole alloys.
Hey, wait a minute. There's another good one. This next one says, great works and great ideas. Again, thank you very much. By the way, do you love playing guitar? It's a creative activity too. So let me see. Hold on.
I'm not sure.
What's in the corner there? Two guitars.
I think Gang and Huaxi.
Yes, I just want to answer the same questions. Do you play guitar?
Listen, I have about 15 different guitars. I used to play guitar.
Wow.
When I was a young man, I played guitar in a lot of groups and bands when I was in Manchester when I was growing up. But I stopped, and then at Cambridge I played. By the way, I don't know if you know, I should tell you this. When I was in Manchester as a young man, a teenager, playing guitar, I very briefly met two well-known groups, the Hollies and 10cc. And then when I was at Cambridge, I met the Who and Pink Floyd, if you've heard of those bands. Those are very famous bands. So I actually got to know them. At Cambridge, I played quite a lot as well. But anyway, I stopped when I started being a serious scientist, when I finished my studentship. I stopped playing guitar in groups and bands, and I stopped playing in concerts and things like that. I played in concerts for about 10 years and played it a lot. But then I stopped. And so for the rest of my life, I've played guitar always for myself. So I still play. One of my projects, which I'm working on at the moment, is I'm trying to do a CD of my playing.
Okay, I'm looking forward to have it.
Okay, yes, thanks.
It won't be very professional. I'm a better scientist than a guitar player, but I'm not too bad at guitar.
Yeah. Okay, so getting late in China at the moment.
Not country. No, mostly it's a mixture of jazz and blues. Jazz and blues.
Thanks, Brian. Really nice to see you and see you in a very good house. And thanks for the very mind-opening sort of thinking presentation, and also the wisdom about not only about the high-energy alloys, not only about the alloy, but the whole materials. Of course, I keep telling the students, polymers are very different from alloys, because polymers are semi-crystalline, so there's something else. But ceramics, metals are very much like, as you comment, sort of like more start to get unified, as you said, the alloys. So thank you very much for the great talk. And I'm thinking maybe a few months later or sometime we might have some kind of like a mini symposium about the alloy theory or something, like informally, somehow with the sort of a discussion, and someone from the audience might give mini talks, like 10 or 20 minutes talks to share, to see this great field. And also, I'm very happy to hear that you're writing the book on Cantor alloys, high transfer alloys, which might be slightly different from, Professor Murty's book.
It will be different. It will be different.
That's very,
because it has a bigger picture. It's got the high. It includes, as I say, the history of alloys generally, and it includes a sort of perspective on what alloys we need as well. So I want to put them in the context of the big picture, because the truth is we have done a fantastic job technologically by developing new alloys. So it's not hydro. The thing that excites me is multi-component systems. There's millions more alloys, and so we need. The future is in these new alloys.
Yeah, that's true. Yeah, thanks. So
Anyway,
let's tell you
can
that.
Can I finish by thanking you for organising the seminar? Thank everybody who joined for listening, and I hope you enjoyed it.
Yeah, thank you. We have like thank you very much.
Thank you, Brian.
Yeah, Brian's great. Yeah, really great to see you. So yeah, hope all keeping well, and yeah, hope the international traveling will be resumed soon. So we see you in Hangzhou in China.
Yeah, we look forward to your trip to coming to. I suppose towards the end of this year, after everybody got the immunization, you know, probably people can travel. I think
maybe next year. Maybe next year.
Yeah, like next year. Yeah, that's true.
Healthy and safe.
I'm missing the good Chinese food. I'm missing.
Yeah.
Oh, yeah,
You will have it.
You only come to China to taste the real Chinese food. I suppose the in Oxford you.
Yeah.
Okay. We'll see you, Brian.
See you, Brian.
Thank you.
Bye bye.
Great. Take care. Take care, Brian.
Bye, Carl.
Bye bye.
再见 ，GK。太棒了。
走啦，拜拜。